AC electric motors are electrical devices that convert electrical energy into mechanical energy. They are used in many industries to drive a wide variety of machines and mechanisms. They are also widely used in the household appliances we use every day. For example, they are used to power washing machines, dishwashers, refrigerators, vacuum cleaners, food processors, and air conditioners. How does an AC electric motor work? In this video, we will examine the operating principle of such a motor in detail using 3D graphics. An electric motor utilizes the principles of magnetism and electric fields. What causes an electric motor to rotate? Imagine an electromagnet. It has a coil and a core. Only when an electric current is applied to the electromagnet does it become an electromagnet. Like a simple permanent magnet, an electromagnet has poles, conventionally north and south. Likewise, all magnets have a magnetic field. It is precisely this magnetic field that is the force causing the electric motor to rotate. Like poles of magnets repel each other, while opposite poles attract. This is clearly visible when one of the magnets is attached to a rotating shaft. And if the direction of the current in an electromagnet is reversed, its poles will switch to the opposite. Therefore, the poles of a magnet and an electromagnet will interact. Opposite poles attract, while like poles repel. In the standard electrical grid that we use, the current is alternating. Alternating current changes direction many times per second. This happens so quickly that a magnet attached to an axis does not have time to turn. Three-phase electric current consists of three phases and a neutral. There is a single neutral for all three phases. Three-phase electric current also changes direction many times per second, but it has an interesting feature. If we visualize a single cycle of the current's direction change, then in each phase, these cycles are shifted relative to one another by 1/3 of that cycle. This shift is created somewhere out there, at power plants and transformers. If we plot the current oscillations in the three phases on a graph, the graph will look something like this. The graph clearly shows the phase shift in the oscillations for all three phases. The operation of an AC electric motor relies on the phenomenon of electromagnetic induction. Let's examine this phenomenon. This is a bar magnet. Let's place a metal frame inside the magnet. Let's start rotating this frame. When the magnetic field lines are crossed, an electric current will appear in the frame, Faraday's law. This current in the frame will be alternating. The faster the rotation, the stronger the current. The frame thereby becomes an electromagnet whose poles change. If we rotate a magnet around the frame, the same thing will happen. This is the phenomenon of electromagnetic induction. But if we rotate the magnet and the frame together, nothing will happen. Because the frame does not cross the magnetic field lines. No intersection of the magnetic field lines, no electric current, no electromagnetic induction. In an AC electric motor, the stator electromagnets are arranged at an angle of 120 degrees. Simply put, the circle along which they are arranged is divided into three parts. This is done because the cycles of current direction reversal for the three phases are shifted by three equal parts. With this arrangement of electromagnets, the maximum values of the fields and current will alternate one after another in a circle. Conventionally, this can be considered a rotating magnetic field. This field rotates in a circle, following the peak values of the fields in each of the three phases. What if we place a metal frame in this rotating magnetic field? Let's consider what happens to a single frame, for simplicity's sake. The rotating magnetic field of the stator generates an electric current in the frame. The electromagnetic field that appears in the frame begins to interact with the rotating field of the stator. The frame begins to rotate, following the rotating field. A brilliant solution. The field created another field, which in turn converts the force of the electromagnetic field into mechanical energy and performs a rotational motion. In this case, the rotating magnetic field of the stator will always rotate faster than the frame. This is because if the field does not outpace the frame, the magnetic field lines will not intersect, and the frame will cease to generate current in a magnetic field. If we imagine that the frame's rotation begins to catch up with the field's rotation, the current generation in the frame will weaken. Therefore, the frame will fall behind again. To enhance the generation effect, it is better to use not one, but several frames. When several frames are used, the current generation will be stronger and the rotation will be more uniform. In this electric motor, these frames are combined into a single structure. It consists of many individual bars. All of them are tightly connected at their ends by two short-circuit rings. The result is a single, solid structure resembling a cylindrical cage. Structurally, this is always a single closed system. Such a motor is called a Squirrel-Cage induction motor. Stator electromagnets are often arranged in pairs or symmetrically. This arrangement is necessary to create a uniform rotating magnetic field, in which one set of coils acts as the north pole and the diametrically opposite set acts as the south pole, ensuring effective interaction with the rotor. Key feature of a paired configuration: symmetry. The coils are arranged on the stator core with equal spacing to ensure a balanced magnetic flux. The pairs of coils are connected in series to create opposite poles. A synchronous motor differs from a squirrel-cage induction motor in that the rotor's rotational speed is equal to the rotational speed of the stator's magnetic field. Permanent magnets can be used in the rotor of a synchronous motor. Earlier, for simplicity, we considered the rotating magnetic field of the stator as a single entity. But we actually have three pairs of changing fields. The displacement of these pairs of fields can be visualized as a rotation from one pair of magnets to another. The rotor's magnetic fields will be attracted by the rotating, opposite fields of the stator. The rotor will rotate, following the stator's fields. But in practice, it looks a little different. The stator's field rotates too quickly. Remember, at the beginning of the video, the magnet couldn't keep up with the rotating magnetic field. The squirrel cage can provide the initial rotation to the rotor. The Squirrel-Cage accelerates the rotor's rotational speed, and the permanent magnets can now interact with the rotating stator field normally. The rotor's rotational speed equals the stator field's rotational speed. The Squirrel-Cage does not function in this case, because the frame itself will not intersect the magnetic field lines. Electromagnets can also be used in the rotors of a synchronous motor. The rotor of a synchronous motor has an excitation winding with an independent power supply. A direct current is supplied to the rotor winding through slip rings. Each individual winding acts as an electromagnet. The electric motor then operates similarly to a permanent magnet motor. These motors have a rather complex design due to the presence of a brush assembly. Additionally, they require an external DC power source to operate.